So as the title says, in this section we will look at solving equations, both exponential and logarithmic equations. We're going to start with exponential equations. And so basically I would say an exponential equation is any equation in which the variable that you're trying to solve for is in an exponent. Okay, they can be more complicated than this. This is kind of your basic exponential equation. And so the answer is whatever power of 7 would give me 25, which is not a whole number, so I can't just guess that. And so what we're going to have to do is use logarithms. Now if you were taught, you could use log base 7 of both sides and do change of base, or use a calculator that can do that log. If you were taught that way, that's fine. I'm going to go by the more traditional approach where we always use natural log or common log, since some calculators can only do it that way. So the key is, by the rules of exponents, if we were to take a log of both sides using any log we want, and I'm going to use natural log so that I can use my calculator, I could apply the rules and drop the power to the front. So I've freed x from being an exponent now to just being a coefficient for the multiplication. And I divide and I have my answer. Okay? So we could evaluate and get that as a decimal, or we just have x as the natural log of 25 over natural log of 7. And I could have used the common log as well, but I chose natural log. I'll point out this is log base 7 of 25. If you took log base 7 of both sides, it would wipe it out and give you x as log base 7 of 25, which by change of base is the natural log of 25 over natural log of 7. I've always preferred the whatever you do to one side, you do to both approach, using either natural log or common log. So what did we just do? Here's some guidelines. So the one we just did, we didn't have to do any special algebra to isolate the exponential expression, but it's really important that we have our base to the exponent isolated before we apply the logarithms, otherwise we can't drop the power to the front. But once you isolate the exponential expression, or if it already is, you take a logarithm of both sides and we apply our rules to bring down the exponent, to drop it to the front as a coefficient, and then you solve the remaining equation for the variable. So here's an example where we do have to do something to isolate the exponential. It's really important. You don't want to just start taking a log of both sides. Okay? First thing you have to do is get the e to the 3x minus 1 by itself. And see, I have it worked out here already in red, but you can subtract 1 from both sides to get you a 16, and then divide both sides by 2, and we wind up with e to the 3x minus 1 equals 8. Then you can take a logarithm of both sides, and here we have the advantage. If we use natural log, it will wipe e out because it's the inverse. So we take the natural log of both sides here, we get natural log of e to the 3x minus 1 equals natural log of 8. The natural log of e to any power is just the power because natural log is base e. They're inverses. So we just get our 3x minus 1 equals natural log of 8. Add 1 to both sides, divide by 3, and there's our exact answer. And if you want a calculator decimal version, just type it into a calculator. Okay, here's one more example of this type of equation. The exponential part's already isolated, so you can go ahead and take a log of both sides. I, again, stuck with natural log. If you like common log, use it. You drop the power to the front. This time the power is not just x, it's x minus 4. I drop the entire power to the front, put it in parentheses to show it's the whole thing, times the natural log of 5 equals natural log of 16. And then we have to solve for x, so we would first divide by natural log of 5. And then in the end, since that's x minus 4, we add 4 to both sides. So we get natural log of 16 divided by natural log of 5 plus 4. Or again, if you're a person that likes to use change of base, that's actually log base 5 of 16 plus 4. Okay, the types that I just looked at are what I would consider to be your basic exponential equations with a single exponential expression you can isolate. We will look at some that get a little more complicated, and one type you can actually solve by factoring. And the most common type of factoring is actually to remove the greatest common factor. And whenever you factor, it's really important that you set one side equal to 0, so I'm going to subtract the 50x, e to the x from both sides to get 2x to the third, e to the x minus 50x, e to the x equals 0. Now both terms have an e to the x, but I can also factor out 1x, since there's just an x here, and 2 divides into 50, so I can take out the greatest common factor here, 2x e to the x. When you remove that from this term, you've taken out the 2, you've taken out one of the x's, so you're left with x squared, and you've taken out the e to the x, so you're just left with x squared. Here you've taken out the x and the e to the x, and you divide by 2, you have a minus 25. Set each factor equal to 0. 2x equals 0 gives me 0 as a solution. I'll jump over here. X minus 25 equals 0. Give me plus or minus 5 when I solve x squared equals 25. Don't forget the negative 5. And then e to the x is actually never 0. It doesn't produce any extra terms. It's kind of like the 2. It's just a positive value that you could just divide by and drop because e to the x is never 0. So the only solutions when we set the terms equal to 0 are 0, 5, and negative 5. So we have a solution set with 3 numbers in it. Okay, there's another type we can factor that are what we call quadratic in form. They look a lot like a quadratic equation with a term in the middle and a constant and a square term, but it's not just x and x squared. But in a lot of ways, if we look at just the numbers, the coefficients 1, negative 7, and 12, this is similar to the quadratic equation, 1x squared minus 7x plus 12, but it's got e to the x in the place of the x. And you'll note that e to the x squared, you multiply the exponents, is e to the 2x, so this is the square term. So if you like, you could use substitution if you want to do that, if it helps you to see it that way. So you can take this piece in the middle and let that be some other variable. I've called it t. So if t is e to the x, then t squared is e to the 2x, and I can substitute in. So I have e to the 2x is t squared minus 7t plus 12 equals 0. And then I solve for t, which is just a quadratic equation. I could use the quadratic formula, completing the square, or this one will factor into t minus 3 times t minus 4. Set each of those equal to 0, we get t equals 3 and 4. However, we wanted to solve for x, not t, so we have to go back and know that each t was e to the x. So we have e to the x equals 3 and e to the x equals 4. Those are small exponential equations you can solve instantly by taking natural log of both sides. Because again, natural log of e to a power is just the power because natural log is base e and they're inverses. So when I take natural log of both sides, natural log and e wipe out. I get x is natural log of 3. Over here, x is natural log of 4. Okay. So I can solve these like a quadratic. You could even use the quadratic formula with 1, negative 7, and 12, and you'll get 3 and 4. But each of those are actually e to the x, this term in the middle.